Hello, grade 11s. Today's lesson is on stoichiometry. It's a mouthful of a word, but it basically just talks about the quantities, the how much part of chemical reactions. If I'm reacting two substances together, you might want to know how much of each you need and how much product you're going to get. That's what stoichiometry talks about. When we look at a chemical reaction, there are three pieces of information that we get from that sentence. We know which reactants are involved, we know which products are formed, and once we've balanced the equation, we know the relative amounts of each. So the coefficients from the balancing tell us the relative amounts of products to reactants that we needed. Remember at the beginning of this unit, we practiced balancing equations? Well, now we're about to see why. Consider the following equation. This is the equation for the production of ammonia. This is the same reaction they do down the street at Koch Industries. In the production of ammonia, we see that nitrogen gas, remembering nitrogen's diatomic, reacts with hydrogen gas, also a diatomic molecule, to produce ammonia. NH3 is the ammonia molecule. The balancing has one nitrogen reacting with three hydrogens to produce two ammonias. But when I say 1, 3, and 2, it's 1, 3, and 2 what? We know that this balancing could talk about molecules. One molecule of nitrogen reacts with three molecules of hydrogen to produce two molecules of ammonia. Or we can multiply molecules by Avogadro's number by 602,000 million, 602 hexillion. And we can then say that 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. Those relative relationships, 1, 3, and 2, allows us to do a transition from talking about the amount of nitrogen or hydrogen or ammonia we have in relation to the others. Once an equation is balanced, we can transition from talking about one molecule to another one. For example, how many moles of hydrogen would I need to use if I start with 1 mole of nitrogen? Well, we can tell from the balancing when you start with 1 mole of nitrogen, you get to use 3 moles of hydrogen. We could set that up as a little factor label line, however. We know we have 1 mole of nitrogen gas, and if I draw a big long line and cut that off, I could get rid of the words moles of nitrogen gas and change it to the words moles of hydrogen gas. Remember, we're always putting the unit we're getting rid of on the bottom and the one we want on top. When our top and bottom relationship is moles to moles, this is where we use the balancing in the equation. Beside nitrogen is the number 1, so beside nitrogen I put the number 1. Beside hydrogen is the number 3, so beside hydrogen I'm going to put the number 3. This way the words moles of nitrogen will cancel, and I'll be left with moles of hydrogen as an answer. 1 times 3 divided by 1, is 3 moles of hydrogen. Now that seems like a lot of work for something you could just see, but we're going to use this molar ratio, the ratio between the two different species we're talking about, in many places in stoichiometry. If I were to start with 2 moles of nitrogen gas, again I want to get rid of the word moles of nitrogen, change it to moles of hydrogen. And again, beside nitrogen's a 1, so beside nitrogen I put a 1. Beside hydrogen's a 3, so beside hydrogen I put a 3. 2 times 3 is 6, divided by 1 is 6. Moles of nitrogen cancels, and my answer comes out in moles of hydrogen. We need 6 moles of hydrogen. And we could do the same thing if we were starting with only half a mole of nitrogen. In this case, we need 1.5 moles of hydrogen. Now, this is the only time that we might see a number other than 1 beside the word moles in one of our truths. And the reason for that is we're always comparing the two species we're talking about. The one that is starting point, the one that I know, and the one that I'm trying to get to, the one that I want. We're doing a relationship between moles of one species and moles of another. Remember this picture from our lesson on 3-step conversions? In the center of the picture was the word moles. We could go from liters or grams or particles to moles and then to any of the other three. We're going to use this picture and the understanding that we just have about molar ratios to do a full stoichiometry question. Consider the possibility that we want to know how much chlorine in grams is needed to react with 10 grams of sodium to make sodium chloride. We will always, with questions like this, start with our balanced equation, and it's important that the equation is balanced. So we know sodium's not diatomic, so its symbol is just Na. Chlorine is diatomic, so it's reacting with chlorine. We put plus Cl2 to produce NaCl. When we do the crisscross between sodium and chlorine, +1 and -1, the formula is NaCl. Once we balance this equation, we get a 2:1:2 ratio. 2 sodium atoms react with 1 chlorine molecule to produce 2 sodium chlorides, or 2 moles of sodium atoms react with 1 mole of chlorine molecules to produce 2 moles of sodium chloride. At this point, what I want you to do is draw me a little picture. We're going to draw me a little kind of a square arrow path. And that path is going to help us to set up the entire equation. I want to start by going, what do I know? In this equation, what I know is that we have 10 grams of sodium. That's my starting point. So right here under sodium, I'm going to put that we have 10 grams. So here we're going to have 10 grams of sodium. What I'm trying to find is how much chlorine in grams. So what I want to find underneath the chlorine, I want to find out how many grams I'm going to have of the chlorine. How do I connect them? Well, we know that I can connect sodium to chlorine in this balanced equation by first converting to moles. Using our little 3-step conversion process, I'm going to go from grams of sodium to moles of sodium, use that conversion, that molar ratio, to change that to moles of chlorine, and then finally go to grams of chlorine. In order to get from 10 grams of sodium to however many grams of chlorine we're going to need, we're going to use our starting point, 1, first change it to moles, 2, use our molar ratio to change it to moles of chlorine, 3, and then use the molar mass of chlorine to change it back to grams, 4. We have used all 4 corners of this little arrow. Our factor label line then will have 4 sections to it. So you can start by drawing a big long factor label line that has 4 sections to it. Each of the sections in the factor label line is going to correspond to one of the 4 corners that we have labeled here. We're going to start with our grams of sodium. Then we're going to change grams of sodium into moles of sodium. We're going to change moles of sodium into moles of chlorine, and we're going to change moles of chlorine into grams of chlorine. 4 steps. Let's take a look at how this is going to look. So start with what you know. We know that we have 10 grams of sodium. That's my starting point on the line. We're going to first step, the first part on the pathway says to change that to moles of sodium. So to get rid of the words grams of sodium on top, I write grams of sodium on the bottom. To change that into moles of sodium, I write moles of sodium on top. That's how I get from where I am to the first point I want to go to. Moles to grams is molar mass, and when we're doing molar mass, we always write 1 beside the word mole. How much does 1 mole weigh? Well, on the periodic table, 1 mole weighs 22.99 grams, and for our purposes, to keep it simple right now, we're just going to say 23. Now, sometimes kids say, don't I have to put a 2 here? No, you don't, because molar mass is always how much does 1 mole weigh? Well, grams of sodium here will cancel grams of sodium, which means that the units that are remaining would be moles of sodium. I'm at this point on the line. We've gone from my 10 grams to moles. My next step on the line is to change that to moles of chlorine. Well, what's a mole to mole ratio? A mole to mole ratio is our ratio that we just learned about. It's called our molar ratio. So to get rid of the words moles of sodium on the top, I write those words on the bottom. To change it to the words moles of chlorine, I'm going to write those words on top. Now this is the place where we use the numbers from the balancing. This is the only place where I use the coefficients in the balancing. Other than that, you do not need to use them. So in the balanced equation, beside sodium's a 2, so beside moles of sodium I put a 2. And in the balanced equation beside chlorine is a 1, so beside chlorine I put the number 1. We are now at step 3. We have used 3 sections on our factor label line. Moles of sodium is cancelled. I'm at the point of moles of chlorine. We're still not done though, because the question wants us to find grams of chlorine. I have one more step to go, so my factor label line will be one more section long. To get rid of the words moles of chlorine on the top, we write those words moles of chlorine on the bottom. I'm going to change it to grams of chlorine. So when I do the molar mass, I need to be careful because chlorine is Cl2. So if each chlorine weighs about 35.05, then 2 of them is 70.1 grams. Now moles of chlorine on the top cancels moles of chlorine on the bottom, and the only units that I haven't canceled out entirely so far are the units for grams of chlorine. So multiplying numbers we find on the top of the line, dividing any numbers that we find on the bottom of the line, and the order doesn't matter. So on your calculators, if you want to try this with me, 10, this is on the bottom, so we go divide by 23. This is on the bottom, so we divide by 2. And this is on top, so we go times 70.1. And the number we get is 15.23. And the only units we hadn't canceled were grams of chlorine. So if I react 10 grams of sodium, I will need 15.23 grams of chlorine. Now this question could have asked me to solve instead of for grams of chlorine, because it's a gas, it could have said liters of chlorine, and I could have rotated this around and used the number 22.4 to change between moles and liters. It could have asked me for the number of particles, and I could have rotated that again. So this little Y diagram actually spins on its axis to allow us to solve for whatever we're looking for. Now again, a lot of places and a lot of textbooks and websites like to use the times sign in between here instead of a vertical line, and that's absolutely fine. It means the same thing. And a lot of times kids like to do one step at a time and just solve for the answer and then use that answer for the next step. Again, if that makes more sense to you, you can. But the steps in the order that you solve them in will be the same. So here's another example. How many moles of ammonia would be produced if 0.6 moles of nitrogen reacts with hydrogen gas? Now, we're assuming we're going to have more than enough hydrogen gas here. We'll have whatever we need. So because we're assuming we'll have more than enough, we're saying that how much ammonia we get is determined entirely by the nitrogen. We know nitrogen. We're asked to find ammonia. We call nitrogen then a limiting reagent because it will limit how far the reaction can go. So we're going to draw a line again as our starting point. I've got my balanced equation here in green. We're going to draw a line from what I know to what I want. I know nitrogen. What do I know about it? I know moles of nitrogen. Now on my little diagram, you notice where moles is. It's in the middle. What I'm asked for is moles of ammonia, again, in the middle. So grams or liters or the number of particles are always the end point of this little arrow diagram. The central point is moles. So in this particular case, we are given moles and asked to find moles. Of this little diagram, we only need 2 spots. My factor label line will only have 2 sections. So if I was given grams or liters or particles, I would have yet another section. Drawing this little arrow from what you know to what you want actually allows you to know how big of a factor label line you need to set up. So we're only going to need 2 sections on our factor label line. I draw a factor label line with 2 sections. Start with what you know. I know 0.6 moles of nitrogen. I want to get rid of the words moles of nitrogen. so I'm going to write them opposite. I write it on the bottom. I'm trying to change that to moles of ammonia, so I write the words moles of ammonia on top. Moles to moles, the numbers come from the balancing. In the balancing, beside ammonia is the number 2, so beside moles of ammonia, I write the number 2. In the balancing, beside nitrogen, I don't see a number. And you remember that when you don't see a number, we assume it's a 1. So beside nitrogen, I'll write a 1. Now the words moles of nitrogen will cancel each other. We're going to be left with the words moles of ammonia, which is what I want. So what do we do with the numbers? Multiply numbers on top and divide on the bottom. Since timesing and dividing by 1 is irrelevant, 0.6 times 2 is 1.2. 1.2 moles of ammonia will be formed. In this third example, I give you the balanced reaction for the reaction between sulfur dioxide and oxygen to form sulfur trioxide. We can see that 2 sulfur dioxides react with 1 oxygen to produce 2 sulfur trioxides. In this question, they give us 19.8 liters of sulfur trioxide. We're actually going to start here at 19.8 liters. Where are we trying to go? Well, we're trying to go to liters of oxygen. So we're going to go from liters of sulfur trioxide to moles of sulfur trioxide. And then, using our molar ratio, we're going to change that into moles of oxygen gas. And then, using our relationship between moles and liters, I can change that into liters of oxygen gas. We're going to go from liters to moles to moles to liters. Now, the direction that we move is irrelevant. Just because the equation has an arrow pointing this way, that just tells us this is what's being made. This little picture just tells us the order to set up our factor label line. On my factor label line, I see that I'm going to need 1, 2, 3, 4 sections. So I draw a factor label line that has 4 sections. Start with what you know. I know 19.8 liters of sulfur trioxide, so I write that down. It's important that I write down the chemical symbol for sulfur trioxide because at some point I end up talking about a different gas and I don't want to mix this up. To get rid of liters of sulfur trioxide, I write that on the bottom and I'm changing it first to moles. In this case, I'm using the relationship that we've learned between moles and liters. 1 mole is always 22.4 liters. So we're at the point where liters of sulfur trioxide has canceled and I'm at moles of sulfur trioxide. We are right here. I next want to change this into moles of oxygen. So to get rid of moles of sulfur trioxide, I write it on the bottom. I'm going to change that to moles of oxygen, what I want, so I write it on top. In this case, I use the balancing. In the balanced equation, beside oxygen is the number 1, so beside oxygen I'll write a 1. And beside sulfur trioxide is the number 2, so beside SO3 I write the number 2. You'll notice the words now, moles of sulfur trioxide, cancel, and I'm at the words moles of oxygen. I'm right here on my diagram. Again, I'm not yet done. That's not the units I'm asked to solve for. So to get rid of the words moles of oxygen on the top, I write those words on the bottom, and I'm changing it to what I want as liters. Again, the relationship between moles and liters. 1 mole is 22.4 liters. So moles of oxygen is canceled, and the only units that we haven't canceled yet are liters of oxygen. That's the units I was asked to solve for. That's how I know I've set this problem up correctly. Again, multiplying numbers on the top of the line and dividing numbers on the bottom gets us to an answer of 9.9 liters of oxygen being formed. Now, this scale of doing stoichiometry problems takes a lot of work. There's a bunch of problems that you can take a look at and more examples that have been worked out for you in your textbook on page 374. But in your workbook on pages 41 and 42 of your green stoichiometry workbooklet, there's a series of questions that you can do. If you have any problems with any of them at all, shoot me a message and I'll post up an example of how to solve them for you. This will probably take us a couple of days to get through. So my plan is for us to be working on stoichiometry problems until we feel that we have a good grip of them.